Hello guys, now here I'm going to be giving you a very unique method for finding the time period of oscillation of a block which is connected to maybe one spring, two spring, multiple springs, maybe pulleys could be part of the arrangement, and you need to find the time period of oscillation of a block. So this particular method involves knowing how to write very simple expressions for energy stored in a spring, and how to make use of energy stored in a spring and replace the complex spring arrangement of the present situation to one single equivalent spring. So it's a very beautiful way this works. So I'm going to be presenting you my way of replacing multiple springs into just one equivalent spring to get the time period of oscillation of a block. We'll start off with a very simple scenario. I'll explain the method and you can see how this particular method could work wonders in whatever complex situation you are going to be coming across if you have one single block and you need to find the time period. So this method could be used as a very short way of approach to save some time in JEE main and NEET examinations. Also, the idea behind this is very important even for JEE advanced, how we think and replace really complex spring arrangements to a simple equivalent spring to get the time period of oscillation of a block. Right, so let me present it to you. I'll give you a few examples to illustrate how to apply these aspects, and once I give you one or two examples, after that you will be able to manage any complex situation. There are questions based on this idea in Irido you will find the question, but then you don't find these short methods of approach as solutions anywhere. I'll just present you my way of how to replace equivalent springs to multiple springs to one equivalent spring, right? So let me just share it, and let me share my working screen and let's get into the discussion right away, guys. Yeah, so the idea behind this method requires you to know simple expression for the energy stored in a spring. Suppose if you have x elongation in a spring with spring constant k, we write the energy in that spring as half k x square. Now, instead of using the expression for energy as half k x square, now suppose say in this spring you have a spring force of F. We very well know that F will be equal to k times x, and we will get the expression for energy in terms of the force. So we can write it as half k. In place of x, I'll put F by k whole square. So energy in this spring can be written as F square divided by 2k. Whether it is in elongated state or in compressed state, with spring force F and k being the spring constant, the energy stored in a deformed spring can be represented as F square divided by 2k. And suppose say now you have an arrangement like this, where I'll take a simple case where there are two springs connected one after the other, and that is connected to a block, and that block of mass m, spring constant k1 and k2. Let's say that block is on a smooth floor, right? So I'll just bring that diagram below for you to have a full view of what is happening. So let me quickly present you this method, how it is nicely going to work. Now what we'll do is we will replace this particular set of two springs with one equivalent spring. Now you know that this can be written using series parallel and all that, but the series parallel and all would not work so nicely in little more complex arrangements. So just first follow the method, and then I will present you complex scenarios where you can see how this method is really going to work wonders. So you see, what I'm going to do is I'm replacing the set of two springs with one equivalent spring. I'll call that equivalent spring as, let's say, having spring constant k dash. Now when this block is displaced by some amount and let's say it is oscillating, there will be some force which is exerted by the spring on that particular block. I'll indicate that force with T. So in both the springs, in the right spring as well as the left spring, you are going to have the same tension. That is because these two springs are connected at the same location, and that is a massless spring. So whatever spring force is there from the spring on the left and the spring force which is there from the spring on the right, those two spring forces, they must balance each other out, right? Because the mass of this location is tending towards zero, net force on that should be zero. So you will have the same spring force in both the springs, right? And now, when we are replacing that K1, K2 with one equivalent spring, there must be exactly same force which that spring exerts on this particular block, so that whatever oscillation nature is there for the block with the two springs present, no, even with the single spring present, you must have the same kind of oscillation characteristic for the block. So there must be an identical force which is acting on the block in the previous case and this particular case, that I'm calling it as T. And also when you replace the two springs with an equivalent spring, the energy of the arrangement, that should not get affected. So whatever total energy is stored in this set of two springs, that much energy should be stored in the single equivalent spring. So we can write T, I'll write it like this, T square divided by 2k1, that is energy of the first spring, T plus T square by 2k2, energy of the second spring, added together. This should be equal to T dash square divided by 2k dash. So sorry, not T dash, it is T only. So T square divided by 2k dash, and you cancel T square and 2 on both sides, you will get 1 divided by k dash equal to 1 by k1 plus 1 by k2. And the time period of oscillation for this particular block, it can simply be written as 2 pi root of m divided by k dash. So this is a simple arrangement for which you would have already known how to write the effective spring constant. Now see, I'll increase the complexity of the arrangement and see how this method will give you the expression for time period in a jiffy. You will be able to get the expression. Now suppose say you're going to have a support and there is a pulley like that, and you are going to have a scenario where let me consider a situation like this. There is a spring, so here there is a fixed support, and then there is another block, sorry, another pulley, and there is a block here like this. So this arrangement is let's say set into oscillation, and you want to get the time period of oscillation. So first of all, note that a time period of oscillation of a spring block system, when you are going to have oscillations in a straight line for the block, maybe horizontal or vertical, the time period of oscillation does not depend on acceleration due to gravity. So you know, even if you have a single spring connected to a block of mass m, spring constant k, the time period of oscillation for that will be 2 pi root of m by k. So what we are going to say is, um, in this string, let's say there is a tension T which is acting on that particular block, and in this spring there will be a tension of 2T. If you apply net force on this pulley to be 0, so here there is T, here there is T, so the spring must be exerting a 2T force on the pulley. So in the spring there is a spring force of 2T. So now what I'm going to say is, equivalently, this pulley, springs, strings, everything which is there, equivalently we can simply replace that with one single spring of effective spring constant k dash, which is going to exert a force T on this particular block. Because whatever force is there on the block which is oscillating, the same force this equivalent spring must exert on the block, so that the oscillation characteristic of the block, the time period does not change. And um, we can now write the energy stored in the spring which was there. I'll call spring constant as k for the original spring. So we can write 2t the whole square divided by 2 times k. This will be equal to t square divided by 2 k dash. So from here we are going to get k dash will be equal to k divided by 4, and hence the time period of oscillation, that is root of 2 pi m divided by equivalent spring k dash, or it is 2 pi root of 4m divided by k. That will be the time period. So likewise, I can even do for one more arrangement. So you see, I'll give you an arrangement here. So you can in fact very quickly now get the expression for the time period of oscillation. So let's say you have a scenario where there is a pulley and you have a spring over here, and this is connected to a block of mass m. That spring constant is k. You have to find the time period of oscillation. So to quickly do that, in this you assume tension T in the string connecting the block. So from FBD of the pulley, you can say that the tension in the string which connects it to the spring, in that the tension will be T by 2, or the spring force that is going to be T by 2. Now you replace this with one equivalent spring connected to the block and call the spring constant as K dash. In this the tension must be T, right? So don't put T by 2, because whatever force is there on the block, that much force this equivalent spring should be capable of exerting on the block. So we'll take that tension to be T, and we are going to say T by 2 the whole square divided by 2k. This should be equal to T square divided by 2 times k dash, or you will get k dash will be equal to 4k, and simply the time period of oscillation will be 2 pi root of m by k dash. So 2 pi root of m by 4k would be the oscillation of this particular arrangement. I'll give you one more. In fact, the questions which I have given you here, to an extent, they can be managed by making the force method. You displace this block by an amount of x, and then you find out the net force on the block, and then show that the net force is directly proportional to this x, and then get the time period. Although that can be done with in the case of the arrangements where you have just one single spring. Now I'll give you an arrangement. You see how this arrangement would be little more complex for you to do if at all you try the spring force method, right? But rather, if you are going to make use of the equivalent spring method using energy, see how simply you are going to get the expression for the time period of oscillation of this particular arrangement. So let's say the spring constants, I'll just give you the values. So consider the case where both the springs are having the same spring constant. So let me assume that T is tension in the string which is connecting to the block. Then the same string passes over the pulley. Here the tension will be T. On the left spring, the spring force will be T, and on the spring on the top there will be 2T force. Then we will replace this with an equivalent spring of, let's say, spring constant k dash, and the mass of this block is m. There must be spring force T, thereby pulling this block with a force of T upwards. Now you use energy method and say that T square divided by 2 k dash, this is going to be T square divided by 2k plus 2T the whole square divided by 2k. So from here you get k dash. Now note that T square and 2 in the denominator, they will get cancelled out. We can write 1 by k dash will be equal to 1 by k plus 4 by k, or we can say that 1 by k dash will be 5 by k, or k dash will be k by 5, and hence the time period of oscillation of this block will be 2 pi root of m divided by k dash. So it will be 5m divided by k. That will be the time period of oscillation. So see how quickly we got the expression for time period of oscillation of this particular block, which is connected to the required set of two springs with the pulley, right? So that's about the idea behind this particular method. Hopefully you will incorporate this into scenarios where you need to find the time period of oscillation of a particular block connected to any arrangement of multiple springs. Okay.